welcome to lecture 16. I posed a problem the last lecture. I don't know how many people had the time to think about it, namely that we started on the problem of triangulation, then I posed this special case, this triangle which I am calling a one. So, this triangle is called a one-sided monotone triangle. So, let me shift to the sample. So, it has to be a monotone chain. Okay. So, one-sided monotone polygon. So, this is exactly one edge, okay, and this is a monotone chain, monotone with respect to the edge. Suppose we were asked to triangulate this particular object. So, it's certainly not as bad as something like nothing compared to this, right. This could be a simple polygon, okay, and if you have some holes inside, there could be more some structure like that, okay. So, from this object, this messy looking thing, I am now resigned to looking at something like this as my first step, right. So, how would you attack this problem? I want to triangulate this. So, since this is monotone, maybe we should just start traversing this chain, right. That would be at least could be a reasonable thing to do. Okay. So, I start traversing this chain, let us call this the base things. So, B1, B2. So, I start traversing from here. Okay. Nothing to do yet, and then I make a right turn. Okay. So, once I make a right turn, can I basically have I found a triangle essentially. Okay. So, maybe I can add this edge. Now, once I add this edge, once this triangle goes out, I am looking at a smaller polygon, right. Again a monotone, one-sided monotone polygon, but with one less triangle, right. So, I can again sort of resume my journey. So, now I again start from here, though this is gone. Okay. So, this triangle is already part of my triangulation. So, I can resume my journey back from this B1 again. I move. Okay. So, just assume that this is not a right turn, but a left turn. Now, if it is a left turn, I can't add this edge because this edge is not guaranteed to be within the polygon, right. So, I continue my journey. Okay. Then I again get lucky, I hit a right turn. Okay. The moment I hit a right turn basically involving the last three vertices I visited. Okay. I join this again. Okay. Now, once I join this, then I should actually again this is taken care of, then I should look at what this is like. Okay. Maybe this is also a right turn. If this is a right turn, then I should join this. Okay. And well, this also happens to be a right turn. So, then I find another triangle. So, these are all basically edges that I can add, okay, and I am creating more and more triangles. Right. So, now you get the basic idea, right. So, we just continue on this process, and we are going to generate some triangles. Right. So, the thing is that when we have actually found a triangle, it is good, and when we do not find a triangle, we sort of continue further, hoping that at some point we will get a right turn. And in a bad case, it could happen that we have hit a chain like this. It is a upward convex chain. So, all the way from here to here, we can't add anything, but then at some point it has to go down, right. So, moment it goes down like this, okay, then you can basically you have found all these triangles, right, till basically it is a till a point when this is again a left turn instead of a right turn. Okay. So, the point is that we will be able to, when we reach this point, okay, either we will have a upward concave chain like this, which I can complete with a fan, or I will basically keep generating these triangles with the right turn, and those basically keep going out. So, I am dealing with one less vertex all the time. Okay. So, I am not going to do a formal proof of correctness, but this is what the procedure is. Okay. And what is the time that we have taken for this? N square, n log n, n log star n. How different is this from our Graham scan? I mean, the analysis for Graham scan.
So we don't go back actually.
Well, we do the same thing. I mean, I don't see any difference between Graham scan and this. So, if that is linear time, then this should be linear time. See, you can keep adding a vertex when you are doing these left turns, okay, but then once so you can add it. Let us see, again you maintain store these vertices in a stack, okay. So, but once we hit upon something like this, these vertices disappear, okay, and once they disappear, they will never come back. So, we are going to insert or delete, insert at most once, delete at most once. Okay. So, this should also be linear time. Okay. What I have not done rigorously is a proof of correctness that this will generate the entire triangulation. So, we will have to somehow combine. So, there is a little bit of an inductive proof essentially. So, you have to just, I have given you all the steps, just have to complete the inductive proof here. Okay. So, this is my easy case where it is one sided monotone polygon, okay. But then this brute is far from a one sided monotone polygon. So, what do we do? Okay. So, that is what we will take up today. So, we want to deal with an arbitrary polygon even with holes and somehow reduce this to the case of one sided monotone polygons. Okay. So, for that we will actually revisit our notion of ray shooting. Okay. So, I will, my input now let us say is only a set of line segments. Okay. This arbitrary polygon can be looked upon as a set of line segments. So, I am given a set of line segments, non intersecting, but possibly intersecting at the end points, something of this sort. Okay, let me stop here. So, this is suppose the set of line segments that define that polygon. Right. What I am going to do is from every end point of these set of line segments, I am going to shoot or draw a vertical line, which means that I am basically shooting a ray upwards and a ray downwards, okay, and extend it till it hits another line segment. Then again, for our familiar trick is that we just enclose everything, pretend everything is within a box. Okay. So, we do not have to go to infinity. So, from every end point we shoot a ray upwards and downwards till it intersects, hits another line segment. Actually, there is another one here which I am not drawing. So, this figure, okay, where you have drawn all the vertical, extended the vertical lines, what does it remind you of? Right, exactly. So, if you look at a portion like this, say so, this shaded thing, lightly shaded thing, it's bounded by two parallel lines, okay, on the two vertical sides, and it has a top edge as and a bottom edge. Okay. So, as someone suggested, this is a trapezium, a trapezoid. So, what we have effectively ended up doing is that by drawing these vertical lines, we now have a set of these trapezoids, okay, large number of trapezoids. So, I can number them maybe even. So 1, 2, 3, 4, 5, etc. Okay. So, how many trapezoids do you think we can have, given that we have n line segments, from n line segments? N line segment means 2n endpoints, right. So, we would have drawn at most 2n vertical lines, right, and these 2n vertical lines could have yeah, well, I mean 2n vertical lines would have 4n additional points, right. So, these additional points are, let us say, these things, and that kind of. So, in addition to the initial endpoints, okay, we have at most another. So, initially there were 2n, let us call it vertices, okay, and then to that we have added at most 4n vertices. So, again it is a planar graph, right, this whole structure, the set of trapezoids plus 4n vertices. So, about 6n, a planar graph. Six n vertices. So, how many trapezoids? I'm sorry. Well, if you go by our asymptotic arguments, it will be some big O of n, right. The vertices and faces and edges are all related linearly. So, certainly no more than some constant time n number of trapezoids, but you may actually, and you can probably do a better counting. Can you just think about a.
This trapezoid has 4 sides, right?
Well, some of these trapezoids, for instance, like this one, sorry, like this one, this is a kind of a a special kind of a trapezoid where one of the sides is 0 length. A triangle is also looked upon as a trapezoid. Okay. At most 4.
I mean, every trapezoid has at most 4 sides, right?
Yeah, sure.
So that means you can count the number of by the number of faces, because these trapezoids are faces. So multiply this by 4 one side, and that is the total number of each, count the other side. And from there you can get the equation on the number of faces, right, which is basically the number of trapezoids.
Okay. So, I will leave it as a kind of a relatively simple exercise. So, I would like you to do the counting even without using that Euler thing. So, maybe you can just look at a vertex, okay, and look at how many. So, there is a vertical line that I have drawn to the vertex, and okay. So, maybe I should actually let me define a few things, so that will be useful for other purposes. Okay. So, a trapezoid, let us call it this, okay, can be of the following kinds. Okay, so some observations that we make. Okay, and so one is this kind of a it's a kind of degenerate trapezoid where one of the lengths is 0. So, I am just looking at the shapes of this trapezoid, how are they being basically being defined. Okay. So, other possibilities are that I have something like and perhaps the most complicated would be defined by 4 line segments. Now, why I am distinguishing between these trapezoids is essentially to give you an idea of trapezoid can be defined by so I'm trying to get a kind of a bound on the number of trapezoids, and to do that I am looking at in how many ways a trapezoid can be defined. Okay. So, if you look at this, the first one, so it's a special kind of a trapezoid where it's degenerate. One of the sides is so one of the sides is of 0 length, that is the 2 aligned segments meet at a point. Okay. The second one is defined by 2 line segments. So, the difference between 2 and 3 is that one is the shorter segment is above, the shorter segment is below, something like that. No, sorry, just a moment. No, wait a minute. This is not different. So, so, the difference between 2 and 3 is that the 2 vertical lines are defined by the one of the segments. In 3, the 2 vertical lines are defined by the 2 segments, right. In number 4, the vertical lines are the trapezoid is defined by 3 segments, right. There is a segment, there is an upper and lower segment, okay, and then there is a left, a separate third segment that defines the left boundary. Okay. In the fifth kind, you have the upper and lower segments defining the 2 bounding edges, and the left and the right defining the 2 vertical edges. Okay. And you will be, if you think about it, so the maximum number of line segments that define a trapezoid is given by number 5, right. So, there are at most 5 sorry, at most 4 lines that can define a trapezoid. If you go by this, we can state the following, that the potential number of trapezoids. Okay, I'll just say what I mean by potential number of trapezoids is n choose 4. N is the number of segments, right? Assuming, okay, again our simplifying assumption that no two endpoints lie on the same vertical line. Right. Why am I saying n choose 4? See, the way I have defined the trapezoids here are those trapezoids, those do not contain any other line segments inside, right. These are the kind of empty trapezoid, right. But I could define a trapezoid, let us say using this, okay, and this, okay. And if I drew that, so if I drew this trapezoid, it's just that inside that there will be many line segments, right. But we know that a trapezoid can be defined by a maximum of 4 line segments, and so therefore, I am just saying that potentially there are n to the power 4 trapezoids, right. However, this particular diagram that I have drawn using the rule that I extend the vertical line till it hits the first line segment, with that it is a planar structure, right, and therefore, it has big O of n trapezoids, and I am claiming that there is a simpler method to count where you can basically show the following, that so this is an exercise, show that number of trapezoids is equal to 3n plus 1. So, to get this number, I don't want you to use Euler's formula, anything like that, just do some kind of charging arguments that look at how the left boundary can be defined, how many left boundaries can a single point define, just count it that way. Okay. So, with that you should be able to get this figure. So, it is a fairly small constant, 3n plus 1. If so, this is the number of trapezoids if you follow the rule that we are not going to extend the line segments till it hits the first trapezoid, and this n to the power 4 can come only if you are allowed to draw these vertical lines even through those line segments, and still there can be at most n to the power 4. Why this number is, we'll see later, why it is useful. It is still not a huge number, it is still a polynomial. That is what we should keep in mind, that given n line segments, the potential number of trapezoids is still polynomial by the way we have defined the trapezoids. We won't read it right now, but I just want you to keep track of that. So, here is how okay, and this diagram is called the trapezoidal map. So, trapezoid map, or equivalently vertical visibility map. So, the first question is, how can we compute the trapezoidal map efficiently? That we can do it in polynomial time, there should not be any doubt, right. So, for every point I draw the vertical line, I just have to find out, it is a ray shooting problem. So, I have to find out the first segment that it intersects, right. So, on every vertical line I can actually sort the line segments and I can get all that information, but that will be kind of expensive, maybe n square or n cube, something like that. Right. We want to do it faster. Okay. So, that is the first problem. How can we compute the trapezoidal map efficiently? And second, what is our interest in this problem? Why are we looking at it? Okay. So, I will try to answer the second question first, and then we will make a few observations about the first one. How do we actually construct it? So, what is an application? What are the applications? And in particular, we want to see how is triangulation related to this problem. So, at a very abstract level, both of them, triangulation and vertical visibility map or trapezoidal maps have got something to do with visibility. After all, triangulation also, whenever you are drawing a diagonal, okay, it should not intersect any of the edges of the triangle or other diagonals. Okay. So, it has got some relevance to visibility. Similarly, in the visibility map, of course, it's a direct, it's just the vertical ray shooting. That's certainly a visibility problem. Okay. So, there is some connection, but we will establish a very nice relation between the two problems. Okay. So, what we do, okay, is so let me shift to the other one. Now, when we do the vertical visibility map, we are drawing these vertical things. Now, look at any edge. Suppose I consider this edge. This is the edge, right? And look at all the vertical lines that are getting terminated at this edge. Okay. So, we have actually and let us number them. Let us number them in the order that they intersect. Okay. So, let us call it. So, for this particular edge, this is of course the two endpoints of the edges. So, I start with some one side. So, 1, the next vertical line that intersects that is 2, this one. Okay. Then we have 3 and then we have 4, right, and that is all. Those are all the 4 vertical lines that terminate on that edge. Okay. Likewise, we can define it for every other edge. So, if you look at this edge, okay, you will find again let us say this is 1 prime, 2 prime, 3 prime, okay, and 4 prime. Right. So, on every edge we look at the ordered sequence of the vertical lines that terminate on that edge. All right. Now, these are by definition trapezoids, right. This the region between two consecutive vertical lines, they are trapezoids. Okay. Now, what we do is starting from one endpoint in the order that they intersect, okay, I will just join these diagonals. Okay. So, I joined one with the vertex that generated this vertical line. Okay, the next vertical line is generated by this point, right. So, I will join it with this, okay, and then the next, where there is nothing else, basically it's just the end point. So, I am going to join it with this, right. And I am going to do it simultaneously for all the edges. So, for this edge again, I am going to join it with this, okay, and this is of course by this vertex, and then essentially it ends like this, right. I am not drawing all the diagonals because it's become too cumbersome and clutter up the diagram. So, when we draw these, these green lines, of course this already exists, I do not have to draw it. I claim that, or observation, that there are no intersections between the green edges. Would you believe this? Just stare at it for a while and see why. And perhaps I should also add that, and neither between green edges and given line segments. Okay. Let me try to complete this diagram while you think about it. Exactly, the trapezoids are completely non-overlapping. So, when I am drawing a line segment, it is completely confined within the trapezoid, right. So, there will not be any intersections, all right. And what I have defined, so if you look at this thing, the way I have drawn these diagonals in order of the vertical lines, this region is, what is this region? What kind of a polygon is this region? No, something more than that. Exactly. Yeah. So, this is a one-sided monotone polygon. This is the one side and this is the monotone part of it, because these are all in increasing order. Okay. So, what do? What is the next step? We just triangulate them separately. So, what we have done is by drawing these green diagonals, we have decomposed this figure, okay, into non-overlapping monotone one-sided monotone polygons. So, given a trapezoidal map, suppose we could actually construct the trapezoidal map, or someone gave it to us, gave us this information, then the next step is rather easy. That is, we can actually triangulate each of them in linear time, and so when you sum up all these things, it will still be linear. Because an edge is shared between at most 2 polygons. So, even if you sum it up, it will still be linear. Right? So, the moral of the story is that given a trapezoidal map, right, we can add the triangulation edges in linear time. Right. One information will be required necessary, that is, whenever we are adding these edges and drawing the vertical lines, what is the inside and outside of the polygon. So, with every edge, we should know which is the inside and which is the outside. Right. So, that information, I am not saying that we have to compute it, but that information will be required when we do all these things. So, the vertical visibility map should be consistent with the inside and outside of the polygon. Now, so therefore, the time, one way to triangulate would be compute the visibility map, okay, and then just follow this procedure. But now, how much time do we need to compute the trapezoidal map? And how do we do it? So, this problem turns out to be not very difficult, but it's quite interesting, and there are many ways it can be done. I will introduce a method, okay, which will be it's like a machinery that we will develop later. So, this is a kind of a introduction to that general mechanism of solving many problems in computational geometry, right? And that is the method of what we call incremental construction. So, the generic method is the following. As the name suggests, what you do is we add objects, in this case line segments, right, one after the other, and at the ith stage, we compute the whatever is required, compute the or the map, corresponding to. So, let us say we have actually numbered these objects. X1, X2. Something else. O1, O2, On, okay, corresponding to O1, O2 to OI. So for trapezoidal maps, okay, we start with, let us say, one line segment, and that is nothing but this, right. We add the next line segment, okay. It could be, it could be anything. It could be, let us say, it is this, okay. If it is this, then what do? We have to erase this part, okay, introduce okay. So, this is the trapezoidal map corresponding to two line segments, okay. We add the third line segment, okay, could be something like this. Yeah. So, once it is that, then we have to make some modification, right. Okay. What are the modifications we have to make? We need to remove some of these extensions, okay. It cannot go beyond this, okay, and keep continuing like that, right. So, when we introduce a new line segment, it can destroy some of the existing trapezoids and it will create some new trapezoids, right. So, this is what is called incremental construction. We just pick up these objects or these line segments one after the other and do this. Now, the same thing could also be applied to convex cell constructions. Okay, now we can pretend that we are picking up the point one after the other, and I probably had made a comment like this in the class that we could construct the convex hull in an incremental fashion, which is nothing but I was trying to mimic the insertion sort, right. So, this can be thought of as a general paradigm, where we are going to add these objects one after the other, and whatever is the final the intermediate construction, we must have the correct construction corresponding to that, and then we add the next object, okay, and then we update whatever construction we had to have the correct construction for the next object. Okay. This is, by the way, not a dynamic situation, because these are given to us. So, it is not that I do not know what the next object is. Okay. So, let us not confuse with the dynamic situation where we do not know what the next object is. That is a different problem altogether and could be a harder problem. Here we know all the objects. Okay. We are just kind of pretending as if that we are that they are coming one by one, but we have it available in the first place, and then when we are constructing it, by just inserting the next object and the next object and so on and so forth, and we are never deleting an object. So, it is certainly not fully dynamic, and it is not even like semi dynamic, because as I said, all the objects are available in the beginning, right in the beginning. Okay. So, essentially the cost of this construction is nothing but summation over I, cost of adding the ith object. Cost of adding the ith object is basically updating the so let us say we call it, let us say T's of I corresponds to the trapezoidal map of O1, O2, OI. Okay. So, the cost of adding the ith object is all the modifications required to update T I minus 1 to tau I. This is just writing this summation, but we have actually no idea what this bound would be like. However, you can imagine that this bound could possibly just reflect on it a little bit, could possibly depend in the order that we are going to add the object. Can you think about situations where something could be bad and something could be good, I mean better?
If some segment intersects the
Yeah. So we could exactly. So we could pick up a segment which intersects a lot of trapezoids. So in fact, here when we are looking at this diagram, this third segment that I added actually went through a lot of trapezoids. However, if I had added that trapezoid, that I considered that as the first segment. Okay. So suppose this was the first. The order in which we inserted was 1, 2, and 3. Right. And instead of that, if I change the ordering to, let us say this becomes, I am calling it 1 prime. Okay. Let us keep this 2 as 2 prime and this as 3 prime. Okay. Clearly, when we add the 3 prime, the number of things that are changing is very small, just one trapezoid is getting changed. Okay. But if we add this, the long one, the long one in the end, then more trapezoids could be affected. And it is not necessarily that we should be looking at long and short. It depends really on the actual configuration. The actual combinatorial configuration is what is going to basically make a difference. Okay. The long one, because it actually goes through all those trapezoids. The long one was way off somewhere. It didn't matter how we when we inserted that. Yes, I mean sure. I mean, but the point is, I mean, how do you know beforehand? Which is a good ordering to introduce, good ordering for the insertion. Okay. So all I am saying is that the cost of construction depends on the order of insertions. So it actually introduces another variable in the whole process. Now, how do we know, which ordering should we choose? Okay, and when we don't know anything about these things, what do? Choose a random order, right, and hope that it will take care of itself. Okay, seems to work in many cases. Okay, rather magically. Okay, so let's say choose. So we call this procedure randomized incremental construction. Okay, or RIC for short. Okay. And what do? The first step is that generate a random permutation pi of the objects. Okay. So, let us call this object sigma 1, sigma 2, sigma n. Okay. And insert according to pi. So, then how do we measure the running time of this, so the cost of this? Right. So, you basically take the average over all possible permutations. Okay. So, the expected running time is the average. Okay, so let me just write it mathematically. Summation over all pi, okay, 1 over n factorial is the possible number of permutations, okay, and the time corresponding to pi. Still actually just some equations, nothing really, there is no meat in it at this point. Right. So, why should this be good? Okay, we have to prove it that this is good, and this is something that I won't be able to do today, or maybe in even the next few lectures. But when we address this problem, we will develop a whole mechanism of analysis, which will also be applicable to this trapezoidal map. Okay. So, just for today, just be aware that we are going to the way we are going to construct the trapezoidal map is do a random permutation of segments, okay, and build the map incrementally by inserting one segment after the other, okay, and update the map. That is the way we are going to do it. Okay. And finally, what we will be looking at is the expected running time of this over all possible permutations. It does not depend on the line segments, it only depends on the permutations. Okay. Whatever be the line segments, the analysis that we will do will only just do an averaging over the permutations. It will not matter what the input line segments are. So, it is worst case over any set of line segments. That is the way we will do the analysis later on. Okay. The other thing that I would just draw your attention to quickly is constructing the trapezoidal map also has a byproduct in the form of a point location data structure. Okay. That may not be obvious. How? Or maybe it is to some. Why am I claiming that? Okay, let us go back to this figure again, where I inserted these line segments one after the other. Okay. So, there is some point which we want we want to find out in the final trapezoidal map where that point is located, or in other words what is the answer to the vertical ray shooting. Remember that there are equivalent problems, right. The point location, which subdivision it falls in, is the same as when we shoot a vertical ray, which line segment it hits. So, what I am claiming is that, so before we added this line segment, okay, consider a point, okay, maybe it was this point, right, this blue point. Okay. So, when these two line segments are there, the vertical visibility, sorry, the vertically visible line segment above this was essentially 1. Okay. So, the 3 prime, let us forget about the 3 prime, let us not confuse, was 1. Okay. And the below one, it is in a box, maybe it is just the one that is below. Okay. Now, when we actually added the next line segment, things changed, right, because it actually went through this, and for this particular point, okay, the downward visibility line segment changed, and it could be so for many other points too, okay, depending on what point we are looking at. Okay. But then what is happening is that as we keep on adding the line segment, I am actually developing a superimposition of trapezoidal maps, right. There was initial trapezoidal map of I segments. When I added the I plus first line segment, I obtained another trapezoidal map which is superimposed, and I can think about superimposing these two things. Okay. So, if I again knew my point, my visibility information with respect to the trapezoidal map I minus 1, okay, I can, if I know about the interaction of these two T I and T I minus 1, I can refine that visibility information, exactly the way that we did even in the case of Kirkpatrick's decomposition, right. We thinned down the triangulation, and then we kept on adding triangles, and we made sure that we kept track of which triangles interacts with another triangle. Similarly, here also we are going to keep track of which trapezoid interacts with another trapezoid as we keep on adding line segments. Okay. So, this is sometimes also called the history. So, if you maintain the history of these trapezoidal maps, okay, that thereby basically maintaining the interactions of the trapezoids at level I plus 1, I plus 2, etc., that whole thing is also a data structure. It is a simple data structure for point location or vertical visibility map or ray shooting or whatever you want it to be. Right. So, this is again a generic method that people use for building data structures. When you do the incremental construction as a byproduct, if you store them, actually I do not need to store them if I am only looking at the trapezoidal map. Okay, I only look at tau of n and I am done. But if I keep track of this tau I plus 1 and how they interact, how the trapezoids of these two maps interact, then I also get a data structure, a point location data structure right out of that. Now, the question is of course again that data structure that we get can again be defined by some kind of a level graph, right. Here are these trapezoids of level this is for tau I minus 1, and then I have these trapezoids of tau I and how they actually interact. That will basically give us this give us the point location data structure, right. Same thing again, it is going to interact in a certain way, and eventually we are going to chalk a path through this level graph. Right. However, unlike when we did the Kirkpatrick's decomposition, where we proved that the degree of each node is constant, etc., here we have no such bound. Okay. So, again when we do that full analysis of the randomized incremental construction, okay, we will show you that it actually leads to a very efficient data structure, where we can't prove that every node has a constant degree, but we will be able to prove something like the expected degree will be constant. So, that eventually again but note that here we are not talking about throwing out half the vertices. Okay. Here we are adding one segment after the other. So, we are going from tau I minus 1 tau I all the way up to tau n. Okay. So, they are not log n levels, right. So, they are tau 1 tau 2 all the way up to tau n levels. Okay. So, we are not going to copy these nodes at every level. What we will show is that for any given path, that path will not visit more than about roughly log n vertices, even if we are adding one segment after the other, because what is happening is that these segments are going to only affect things locally. Okay. So, this point of course got affected by this line segment, but it may not get affected by this line segment. It really depends on the order in which we inserted the line segment. Okay. We can have another line segment here. Now, if this line segment 1 was not inserted before, let us say this is number 5, then it will get if we insert 5 after 1, it will not get affected by 5, but we inserted 5 before 1, that will then it will get affected. Okay. So, this I will actually, when we do the analysis later on, I will demonstrate this with the help of actually insertion sort. Okay. Because that again has a similar analysis I can do, and then we will see that actually at any point the chances that it will get affected. I will just give you just an idea. At the ith stage, the probability. So, we'll this right now it will all sound very vague, but let me just mention the probability that the visibility information will change. Okay, is proportional to something like 1 over I. Okay. So, that when you sum up over 1 over I, it is log n. So, this will be the general sort of analysis that we will be able to, or bounds that we will be able to prove. Okay. And but how this probability came and how, etc., these are not that complicated, but very, very clever. Actually, the person who came up with it. So, I will stop here today.